First, I want to welcome you all to the webinar today, and we still have a few people trickling in. My name is Eric Mucklow. I'm the lead architect for energy at the headquarters of the Corps of Engineers, and we will focusing on what we're doing for energy in Army facilities. This is something that we've been working on a while, and some of you have participated in former webinars we've had on different subject matters. This particular webinar is more of an overview of the whole effort, the kind of mission statement, if you will, the strategy that we're going forward with. And so you'll see some slides you might recognize from other topical areas as we kind of go through the different subject matters. So we'll get started. What are we doing? That's the question to ask first. We're doing a lot of things. This image is the future of the Army facilities, metaphorically speaking. This summarizes our strategy going forward, and this is what we mean by that, what I call the coffee pot principle. If you think about a coffee pot, you basically have two traditional technologies. You have the traditional Mr. Coffee coffee maker that many of us use every day, some of us quite often, and you have a insulated carafe, double-walled, air gap in between our insulation. And the difference is similar to how we managed our building design and construction in the past. The Mr. Coffee makes the coffee, and it drips down to the carafe. So it all starts out with hot coffee in both scenarios. But the Mr. Coffee has a hot plate down at the bottom to then add energy back to the coffee that is radiating out through the uninsulated glass carafe. So you can see in the infrared example, the higher temperature range is reflected in the Mr. Coffee, and you see the white hot plate at the bottom. The camera is picking up that hot coffee because, of course, the infrared radiation is just radiating right to the glass. The coffee inside the carafe is just as hot, but you don't see it because it's not radiating out through the insulation. So in similar ways, we're going toward this model for a low energy facility design strategy that instead of continuing to add more energy to our facilities to heat them or cool them, we're going to try to keep the energy that we have in the air once we heat or cool it from the outside to the temperature that we desire. That's with tighter buildings, minimizing thermal breaks. A lot of the principles you may have heard us mention passive house. Passive house is an initiative mainly in Germany and Europe that actually started here in America in the 70s with the low-cal house. Low-cal being low calorie. That was the trend at the time. But they picked up and ran with the concept, but it didn't really catch on to here, and now we're taking it back. So on a building level, these are some of the things we're looking to do as we go forward. We want to do things that are life cycle cost effective. We want to do things that make sense for the taxpayer. I like to say that every dollar we spend was taken from somebody who earned it under pain of imprisonment. Because if you don't pay your taxes, you go to jail. So that gives us a responsibility to do the right thing and not be flippant about what we spend money on. So there are a lot of things that are cost effective energy-wise, and some things that are proposed that are really not. And we're trying to discern the difference between the two. And of course, the tricky ones are the ones that are cost effective in some situations, cost effective in the other situations. And so we get into the it depends answer a lot. Right now we're targeting 40 to 55% savings, and I'll go into how we came up with that number to be net zero ready. And again, I mentioned the passive house techniques, tight building envelopes. Energy recovery ventilation, basically with our exhaust air running it through a energy recovery device, which is essentially an air-to-air heat exchanger, which takes the outgoing air and passes by the incoming air with like metal plates or membranes in between, so that the heat energy and in some cases moisture can transfer between the two. And so you preheat your incoming air with the exhaust air going out. Saves you a lot of energy that way. And again, I mentioned the thermal bridging avoidance. That's basically, if you're going to have an insulated wall, doesn't really make much sense if you're putting insulation between metal studs, which are being highly conductive metal bridges right past your insulation layers. So proper detailing is a good way to avoid wasting money on things that don't pay back because you've essentially given them an Achilles heel. We need to build our technical base in this area, and we're working on that with our engineering and construction labs and getting the word out, like doing webinars such as this one. We're looking more at cost effectiveness, life cycle cost analysis, as well as measurement and verification to prove that we're getting the return that we expect to be getting as we go forward. On an installation level, we're looking at master plans that include energy and sustainability integrated into the master plan as to one design that's comprehensive. It's not good enough, we found, to do an energy study that then gets put on a shelf, but then when the project need comes up, they go to the master plan without dusting off the energy study, and so the energy ideas that are identified don't get picked up necessarily. So that's why we're looking at integrating these things together and having cluster developments, a lot of things that we've had webinars on in the past as well. District energy concepts, making sure that we do district energy right, that the buildings aren't so spread out that you lose all your gains into line losses by the time you get out to the locations. Possibilities of cogeneration systems for central plants. Those are looking at efficiencies rather than 30-40% for a single generation system like a simple heat plant to up to 85% or so for cogeneration systems. Smart grid technology, low impact design, and zero escaping. Those are sustainable techniques to minimize our water usage and impact on the hydrology of the site. And of course, we're looking always at technology and public-private partnerships, and I'll go into some significant movement on those later in the presentation. Most of you have probably heard of our Army Energy Campaign Plan. Basically, the campaign plan, I'm looking at it from an Army perspective, not just the Corps of Engineers, on how we are to try to reduce our energy consumption. We call it energy security is an important point because this is more than just trying to save money, but also being more secure from external influences. As the Army, we are responsible for nation's security as our primary mission, and if we are beholden to external entities beyond our borders, such as unreliable markets, unreliable regions of the world where fuel sources are produced, we can be vulnerable, and we don't want to be able to have our mission compromised by somebody else out there. So we're looking at some energy program tenets from the Army perspective. Conservation, changing the culture. They have a saying over at MCOM, every soldier is a power manager. Helping the soldiers that don't pay their power bills directly be responsible and for their energy performance and what they use, to have an awareness of the resources that they cost the Army as they go about their business and the way they do things. Some changes aren't necessarily anything that affects quality of life. It's just a simple way of doing things differently. In our facility energy, as I mentioned, we're reducing demand as the cheapest way to do it. You don't need is one that you don't have to pay to be produced, because there's nothing that is 100% efficient on turning anything into energy. So everything needs maintenance, et cetera, et cetera. So it's something to do best is to lower your energy consumption first, and then to get to net zero by 2030 as the goal. To try to look at renewable energy systems after you've done what you can to minimize how big those systems have to be. Resilience, as I mentioned, having renewable energy systems on installations can be a way to power critical infrastructure that in the face of severe disruptions, that some of which we've seen in other areas of the world that we've been blessed not to experience as much here, can happen here, and we want to make sure that we're prepared and we can still carry on despite the circumstances outside the fence. This is an example of, I mentioned that changing the culture, first bullet on the previous slide. This is an example of what that might look like. We might end up putting sub-meters on each unit, unit being either a housing unit or a unit of a particular brigade, squad, what have you, that is responsible for their energy and to show them on a daily or weekly basis what their performance is and how much they've saved, how much they've used. And that can be compared to other like units in the Army. So there can hopefully be a bit of a rivalry to save energy and to see who can come in and do the most with the least, and bring attention to things that are running up our bills. So how do we know that this is the right thing to do? Basically, how do we know that these things that we're integrating into our facilities are what's going to get us where we want to go? Like all good government bureaucracies, we commissioned a study, and we had Searle, in collaboration with the Department of Energy and others, look at our 5 most common standard facilities. They looked strictly at the floor plans, their standard floor plans and adjacencies as individual buildings without reconciling any change potential to site conditions. These were independent of any site. So they just looked at the climate regions as though the buildings would be plunked on into that climate without change, other than what could be done to the standard building. There's a copy of that report available on the MSRI site. There's a link to it there. If you want to look that up, it's got a lot of good information of the technologies that they looked at that could be helpful for those of you that are in the design and construction business. And you'll see the little, I don't know if you noticed, but they have the coffee bean theme coming up here to remind us of that coffee pot principle as the theme going forward. So that study basically took 4 packages and did a life cycle cost analysis on different regions and different areas to compare and show us what the lowest energy consumption we could get with different combinations of technologies. Some technologies work better with others. Basically, that's to say, for example, if you want to do skylights for natural daylighting, they only really save you energy if you couple that with dimming controls, preferably automatic, that reconcile the ambient light levels so that, you know, if it's a cloudy day, you have more electric light. If it's a sunny day, you have less electric light. If you're sitting there with your lights on 100%, even though you have skylights, you're not gaining any energy savings. So that's the principle behind that. So this is how the results played out in one of the building types. This is for the barracks, the unaccompanied enlisted personnel housing, and in climate zone 4A, based on the ASHRAE climate zones. You can see the baseline that we were starting with from the 2003 equivalent building, and the red represents the plug loads, the loads that the user is responsible for, and we could only do so much with those because those are a bit beyond our control. But if we look at how much we can reduce what we have in the facility and somewhat reduce with the with the plug loads, you can see they're all equal at 14%, based on Energy Star equipment, that kind of thing. But this is how this particular scenario played out. So we were looking at being able to get down to an energy intensity significantly less than what we would have done a couple decades ago. This is a graph of how those the components that make up how those numbers add up for one of the scenarios, and this shows an interesting phenomenon that is important to note, and I'll go a little more into this and how this sums up. But if we start with our baseline point and we add modifications shown here, added insulation, improved air tightness, that will get us 17% savings on the energy just by doing that. And it'll add a cost impact for the extra insulation and all that of 3.8%. We take that further with our package, and we improve HVAC efficiency, high efficiency pumps, dedicated outdoor air systems and energy recovery devices, those heat exchangers that I mentioned with the incoming outgoing air. That adds another 2.7% to the cost. But then when you come to resizing sizing the HVAC system, you find that, well, if you're not leaking your building every there with a looser envelope, if you're keeping your energy in that you've created, then you don't have to have as big HVAC system. So you can downsize the HVAC system, and that resulted in this case, with a 7% reduction. So here you're at a point where you're getting 38% energy savings and spending less money than what you would have if you had just done it in the traditional way of doing business. So that's a neat phenomenon, and I think that's something that just begs the question of why would anybody be against doing this. Nonetheless, we sometimes have resistance, and we need to march forward and get the word out that this is nothing to be feared. Then we continue to progress toward our goals. Our goal by ESA 2007 is 65% energy reduction from the 2003 baseline by 2015, which of course is what is on us now to design and develop. So 38% is not good enough. So we proceed to go further. We add another 11% savings in this example in our lighting systems at incremental costs, and then we get up to a point with an additional 4% because if you save water, you're also saving energy in pumps and water heating and things like that. So we get to a total savings, and then we continue to add required things that don't necessarily have an economic payback on energy, but add a little more cost to facility. So the net difference in this example again is 5.2% cost increase, but as you can see, that's quite a significant total for energy savings for not a lot of money, and that basically would add up in this example to a payback of 3 years, which is pretty good return on investment. The government typically occupies our buildings for a whole lot longer than 3 years. One study I heard of was 62.5 years on average. So that's something that'll pay for itself over and over and over again. This is an example office building in different climate zones from another study, and you can see we have a certain pattern here. The percentage of savings is across the bottom. As you increase the percentage of savings, then the annualized cost, basically the premise that money you spend now you have to pay a certain amount for as in the total cost of the building, mortgage value, even though of course in the government funding we don't necessarily have a mortgage, but that's the cost of funding essentially. And then you get to the point where trying to get a little bit more savings just gets more and more expensive. This is under the presumption that you're going to start with the lowest hanging fruit, the most return on your money, and then you get to a point where you run out of cheap things to do. Excuse me. So this characteristic curve I like to call the swoosh curve, and it can be characterized by 4 different points that are kind of milestones, if you want to call them that. The first being the baseline, what we would have done in 2003, for example. We add energy savings, we get to about the 25-30%, depending on the building type and the climate zone. We can get to a point where we could have a lower incremental cost, a lower first cost, and have a decent energy return. But then if we keep adding energy savings back to the point where we would have spent the same amount of money in that prior example, 38%, then we call it, this point number 3, that's where the red line crosses the cost line. If we continue to add energy saving measures to get to a point where it doesn't make sense anymore, point number 4, that's what we call net zero ready. And what we just define as not making sense anymore is the balance point where you get to a cost per watt saved of any future energy savings that is equal to the cost of a renewable energy saving system, a renewable energy system per watt. Obviously, to get to a net zero facility, you're going to have to produce energy. So there's a point at which you have to add a renewable energy system. The point at which that makes sense is where the cost of doing anything else to save energy would cost you more than it would cost you just to produce that amount of energy. I hope you understand that concept. Not sure I spoke to it well, but anyway, that's what we call net zero ready. You might have heard that term, and it seems to be something we get a lot of people asking us what we mean by that. And so getting our facilities to the break-even point where we can't do anything or shouldn't do anything more to them to get to net zero without just buying a renewable energy system. That's what we're shooting for. So to summarize what we've learned from that study and from other studies we've looked at, the ESA 2007 targets, it doesn't just end with 2015 65%. It goes all the way on to 2030 at 100%, being fully net zero for our government facilities by that point. And so the next milestone in that law is 2015. But it's a high bar to achieve. It is a high bar because we're looking at 65% as being in this category where it might be cost prohibitive for certain facility types. The math basically includes plug loads, facility loads that are what the user uses. And in something like a dining facility, I think that slide might be next, yes. In something like a dining facility, here we go, the DFAC, you end up with a certain amount of energy used in the process that you can't really reduce no matter how well you make the equipment. If you think about a piece of meat, you get a raw piece of meat and you apply energy, heat, to it to cook it. If you don't apply enough energy to cook it, you're going to end up with raw meat, steak tartare. So that can't be reduced. You can find more efficient ways of delivering the energy to that piece of meat, but there's a certain point where it's just going to take so much energy to turn a raw piece of meat to a cooked piece of meat. And that's just the fact of life. And so meeting the energy savings requirements with the DFACs is a challenge. In the study results, facilities almost uniformly, with the exception of high altitude Alaska up there, latitude, whatever it is, was the motor pool facility, the maintenance facility. There have been advances since 2003 in highly efficient doors and things like that, and they were able to achieve the 65% reduction with their package. With that, the operations facilities and the brigade headquarters, they're getting up there, but they're still not quite to the 65% level. Now, this study again only reconciled what was in the programmatic floor plan. Hopefully, with integrating the site conditions, the solar availability of a particular site, and any other idiosyncrasies about what the architects can do on a case-by-case build basis, is something that maybe can get us to the across that line up to 65% economically. So we need to have a design effort that is more informed, basically letting people know that, hey, you can design a building with greater energy savings and not pay necessarily any more or only a little more than what you would have paid for. And we need to start modeling our buildings and doing life cycle cost analyses and learning, getting some technical skill in learning how to design buildings better, how to design to avoid thermal bridges. Some of these things are more like best practices or design techniques than they are something you buy off the shelf. Energy recovery ventilator, you just spec it and buy it, that's easy. When it comes into something along the lines of thermal bridges, that's more of a know-how kind of thing that you just have to learn. And hopefully we'll be getting that education out to the field as well. We're sharing with what we're doing with the Navy and Air Force, and they're learning from us. We're going in some directions that they're evaluating and haven't got on board with. ASHRAE 109.1 is a standard, for example, and they're doing some things that that they've gone further with than we have, integrating solar, for example, with the Navy and some other things. So the concept is changing the culture. Just like we talked about changing the culture of the soldiers, we also need to change the culture of our design process. Rather than having a minimum design to criteria, we're trying to focus on a culture of design that starts with a charrette process, a brainstorming process, and thinking what's the best way to meet these needs? How far can we take this? Designing to minimum standards basically implies that once you hit the minimum standard, then all thinking stops and you just go forward. And basically that that leaves on the table a lot of things that might be better ways to get to the end goal than the ones that you started thinking about first, and also it leaves on the table a lot of additional savings that we could be bringing to our clients that that maybe was beyond what they thought we could achieve when they wrote the standards or their criteria. So that's illustrated here by the instant coffee, again the coffee, versus the siphon coffee, which I hear is a very good way to make coffee for flavor and a number of other things. I haven't tried it myself. But anyway, so site. Every site needs to be evaluated, and some people call these eco-charrettes. I like to just call them part of the charrette process. There are winter winds that should be blocked and can be blocked with evergreen trees, things like that, that just need to be reconciled. There's summer winds and solar access. What's shading the building at certain times of the year? How can we let sunlight into the windows during the winter and block it during the summer if you're in the northern hemisphere, so that we can get a bit of savings off our heating bills, so that we can block the heat from the sun when we don't want it and accept it when we do want it. And how do we organize our buildings so that we look at a program and say, hey, you know what, we are going to take our occupied spaces and give them the access to the sun and to the views and things on the south side of the building, and put things like mechanical rooms, storage rooms, and things like that on the north face, where we don't need as many windows. There's not the daylight advantage, and windows on a north face wall, if you have a lot of strong winter winds, can be a liability to your building envelope performance. So the bubble diagrams, as the architects out there would be familiar with, are something that need to be laid out with the site access in mind. Another thing we're doing, and hopefully we'll be getting more info out to the field on, is we've been partnering with the Federal Energy Management Program from the Department of Energy, FEMP. They have a group they call Technology Deployment, and they have done a study that looked at a lot of technologies out in the field, and they weighted them and scored them. Their weighting criteria had 3 categories. They had the basis of the energy performance, how much that they would save, the cost effectiveness, and then also the market viability. In other words, they wanted to pick technologies that were mature enough or stable enough in the market that if the federal government, being good stewards of the taxpayer money, embarked on going that route, that we wouldn't be supporting something that was going to be bankrupt next week, or that it had a very limited supply line that wouldn't be able to meet our production requirements. So they basically racked and stacked those, and they came up with the top 20 technologies that are listed here. Some may or may not be as appropriate to our environment. We've already put out an ECB earlier back in April about the exterior lighting, which is something we got off this list. Being LED or solid state, also that can be induction lighting. There's a lot of overlap for exterior lighting. But meeting higher standards with newer technologies that they recommend for us to give us a start. Of course, we need to do our own analysis as the projects go forward. But these are ways that we can at least have a starting point that we know have been put through a first screening that will enable us to ensure that we're doing the right thing, or at least we have a good probability of success. So, why are we doing all this? That was the last question of the title of this presentation. And I would just say it's the right thing to do. But then, well, who says it's the right thing to do? Well, a lot of people do. This is what draws a lot of people's attention. We are using a lot of power. The Army is using millions, billions, whatever, I can't even count that high, mega BTUs in energy. Mostly, proportionally, the largest chunk of that is electricity, 48%, followed by natural gas. And if you look at that, what that boils down to is cost. Natural gas is a lot cheaper than electricity, and so as a cost proportion, electricity is the greater percentage, almost 2/3 of our cost expense. But this is up to $1 billion billion a year. So if we can save 65% of $1 billion, that's a pretty significant savings. That's a lot of taxes we won't have to pay in the future. That's the potential. And so Congress, in their infinite wisdom and the other powers that be, have given us a lot of mandates to say, go out and do this. We want you to do better with what we're giving you. Sorry, there are 55 federal mandates total, at least, and some significant ones on the left-hand tablet. Here are some legislation, executive orders, OSD policy, the memo from Dr. Robine from October 2010 saying that she wants 40% of the points we get in LEED Silver to be from energy and water savings, those things that have payback. There are, of course, a lot of LEED points you can get for things that are good for the environment that don't have payback, but she wants at least 40% to be from that. And then we have Ms. Hammock's memo corresponding to that, saying that we will be fully certified at LEED Silver, and also establishing 189.1. But some of the larger goals, the bigger picture goals that are affecting us in our design efforts and where we're going are on the right here. Energy intensity, that's the amount of energy you use per square foot. Basically, we want a 30% reduction by 2015. And ESA 2007 refers to reducing fossil fuel energy. That's that 65% metric I mentioned earlier. It should be noted, I should have mentioned it earlier, that is regarding fossil fuel produced energy. Energy produced by solar, wind, whatever renewables doesn't count. That is a piece of legislation that was passed to try to curtail global warming specifically, in addition to saving money. Increasing our energy production, we basically are missing our targets on this one. Looking at the overall total of energy that we consume, 7.5% of it by now being produced by renewable sources, and 25% by 2025 was the next level of the goal. So their strategy to meeting that is going forward, and I'll talk about that more in a minute. But that's in conjunction with what we're doing for our facilities. That ESA 2007 I mentioned, the 65% by 2015, and it ramps up all the way to 100% by 2030. That's a very ambitious target, and when and where we start programming these higher numbers are something we need to start thinking about, because those are very high levels. As a tool to help us get there, help us do the right thing, Ms. Hammock, who most of you know as the Assistant Secretary of the Army for Installations, Energy, and Environment, was on the 189.1 Development Committee, and she issued that as a standard when she came in power here. And basically, she did give us some exceptions to the way that the 189.1 is written itself. 189.1 was written for the primary focus of the private sector and one-off developments. And we have some unique opportunities and some challenges that needed to be reconciled. And she coordinated those with us before issuing her policy letter, and I'm going to recap them a little bit. First off was the site selection. The 189.1 development had a tenet of avoiding urban sprawl, and urban sprawl is not really something that is an issue for military developments within our fence. We usually have a fence that's there, and it's not getting any bigger, and we have needs to do things out in forested areas, or areas that 189.1 would define as green fields. 189.1 has some exceptions for green fields that allow development for green fields, specifically for like agricultural or forestry buildings and services. Well, that would not include like a military training facility or something that we do along those lines. The policy says that we will give preference to things that are in the allowable sites, and we will avoid prohibited development activity on prohibited sites unless there's a specific exception from Army headquarters. So that's one of the exceptions to the policy there also. Building water use reduction, we will do achieve the mandatory provisions there with the exception that faucets for sanitation in public lavatories. Rather than being a maximum of 5 gallons per minute, there'll be a minimum of 5 gallons per minute. That's because I don't know if you've heard about the study that showed that for a low flow fixture, you'd have to wash your hands for at least 30 seconds to get them clean. There may be doubt that our soldiers will spend 30 seconds if you count on your watch. That's quite a bit of time to be washing your hands if you're in a large group in a hurry to get through a bathroom. So water site use reduction, we went further than what the 189.1 allows, in that we don't use any potable water for irrigation henceforth. And so those provisions no longer apply to us. That's one of our good saving techniques, and also to encourage the water reuse. The renewable energy provisions, I'm not going to read the whole slide here, but I'll spare you from that. But basically 189.1 has a set-aside amount, a ratio that they want to be produced by renewable means. And in our case, we looked at the installation environment rather than being one-off buildings and said, hey, we can get a better economy of scale rather than having little individual solar systems or wind turbines here and there and every building we build. It would make more sense to take all the requirements of those projects and meet them by one large-scale, utility-scale renewable energy project on the installation or programmatically. And so we do have an exception in the policy that allows that. And basically, we're not going to try to meet that criteria until 2015, FY15, because that takes a bit more planning and processing to be able to plan for those projects. And that is something that's in the works. Basically, on the street right now, there is a solicitation on FedBizOps that closes Friday for the first go around. And basically, it's for a IDIQ contract, indefinite quantity, indefinite delivery contract, that'll collect vendors for a central database that'll have work orders to go out and do a public-private partnership. And that partnership will be a power purchase agreement where we give them the land and say, okay, we want you to build a renewable energy plant on this installation in this area, and you build it with your money, and we'll buy the power from you, and you operate it and maintain it. And that way we get our energy security. We don't necessarily have to do the whole MILCON program funding and all that. It's one of these public-private partnerships. They make money, we get our needs met, and that's a $7 billion scope that they're going forward with to meet that need as to how to get us to our net zero future, at least get us closer to it. So there's the solicitation, if you want to look that up on FBO. I didn't need to actually go there. Okay, there I am. Sorry, I started bringing up a browser on my end. There are 277 vendors listed last I checked, so there's a lot of interest. So that indicates that there might be a good response, and it might be a successful program. So we've got our fingers crossed on that one. Getting back to 189.1, there's been a lot of people asking about it. Congress has told the Department of Defense, thou shalt give us a report on the cost effectiveness of this. Air Force went out and they did a study. It was more like a case study of 4 cases, and they evaluated the cost impact from some projects that they built recently. The Corps of Engineers built for them in some cases here, and these are the results of their study. And they included that renewable energy requirement in their projects, the one that we're skipping until 2015, and that did contribute the largest portion of the cost impact. For example, on this weather agency, the cost added to meet 189.1 they determined to be 7.1%. Of that 7.1%, over half was 4% was the renewable energy component. And the Tyndall Fitness Center, a project which we did, and of course got the Chief of Engineers Award of Excellence, 1.3% cost impact, a full percent of that was just the solar system, just the renewable energy system. Now that achieved a LEED Platinum, and so achieving a LEED Platinum facility with only a 1.3% cost impact is pretty impressive. That's something that we wouldn't have been able to do a few years ago, and I think that shows the maturity of the industry and how we're getting to where energy and sustainability is a part of our standard business process, where it's becoming how we do business rather than something we have to do extra. And again, you can see the cost impacts of these other two facilities that they studied. So the cost impact is not that great, and it's something that's going to pay for itself as we own and operate the buildings from here on out. So how are we meeting our goals? We have some challenges. Looking at the goals as three categories: our energy savings program, our energy reduction, our water reduction, and renewable energy production. The first graph here, energy intensity, that's that energy per square foot. They have a glide path shown in red. That's the getting to that 30% reduction by 2015. If you plotted that out to 2015, you can see we're a little bit above the line. There are some things that are challenges to us, and others are opportunities. One is, if you think about, like, for example, data centers. A data center now can hold a whole lot more servers in a rack with these blade servers and things, so that even if each server uses less power than the same server would have in 2003, if you have a lot more servers in a smaller room, your energy intensity goes up the way it's calculated. So there can be some challenges in meeting that goal. So we need to make up for that in other areas and see if we can get back on track for that metric. We're doing well with water. You can see we're actually ahead of the curve. This is as of fiscal year 2011. We don't have the numbers yet for 12, which just ended, of course, 2 days ago. And the renewable energy program, we are behind in our goal, but when we get that $7 billion RFP out there, IDIQ in place, so we can start issuing RFPs, that's greater than their estimated $1.7 billion investment required to meet the next milestone. So that's achievable. So hopefully we've got some progress going forward in meeting our goals. So at this time, if you want to type any questions in the Q&A block down here, Ryan will sort those and process them, and they should show up on my screen here, and then I'll be able to answer them or something along those lines. Okay. I have this thing shown right. Okay. I'm not seeing any questions at the moment. But oh, and also there at the bottom in the left-hand corner is my email address, and some other notes that Ryan's added. There's also, to be noted, in the lower right-hand corner of your screen, you can see that we have a file share box down there where you can download the presentation if you would like that. So here's a question. Okay, let me see if I can expand this. How are life cycle cost analyses being funded, and are there a range of acceptable life cycle cost estimation techniques? That is something that is to be added into our process. There's not necessarily a set aside funding for that. There is a a life cycle cost analysis center of expertise that's been identified recently that I believe the point of contact's information should be on there. And that's one of the things they'll start looking into is how to standardize the life cycle costing process and how to make sure that we're looking at apples and apples across the board. So that's where that's going. That might be able to get further information from that CX. Okay. Notice the recommendation for super T8s. Why use those versus T5s? That was based on the study that that FEMP did, and they looked at T5s, they looked at super T8s, and that was one of the recommendations that they endorsed as being something cost-effective to implement. The different technologies that were listed were not necessarily at the exclusion of others. But the T5s were not listed, and I believe that they had some manufacturing support analyses going into that as well. If you go on the FEMP website, you can look at the studies and how they scored each thing, and they'll talk about how they determined what was the best thing to do and how each thing scored in those three categories I mentioned, not just energy efficiency but cost effectiveness. As well as the market viability, and so the cost effectiveness might have been something that tipped the scale more toward the super T8s. I don't know the answer to that off the top of my head, but on the FEMP website you can see the whole study behind that. Okay. How about using VE to do life cycle cost analysis? Value engineering. It's kind of a different animal than life cycle cost analysis. Value engineering tends to focus on getting the same performance by a more efficient in terms of schedule or cost. Usually they tend to focus on the upfront cost. That's certainly viable to do things that look at value engineering from a life cycle cost or a total cost of ownership. I think that you'll see more guidance coming along those lines in the future toward the value engineering efforts, specifically that they should not delete things that are put in there for energy efficiency on the basis of first cost. We've seen some decisions made in the past where things were cut based on lowering the first cost at the expense of the operational cost. And we want to try to avoid doing that kind of thing because that will never meet our goals if we do that. Are the file share files located on a website somewhere? Oh. Okay. I was just passing a note to read the questions because some people don't see them. I just got a question that came in. Are the file share files located on a website somewhere? That the energy and sustainability site will have links to the files. There is a file for this presentation right there in the bottom right. You should be able to click on that and download it. But on the energy sustainability website, of course, we just launched that. If you find a page that just says something that looks like it's Latinum, lorem ipsum, something or other, that's just filler text. That means it's still under construction. There's a lot of that right now, but we're working on that. We're getting the centers of expertise and people in the field that will help us, hopefully help us start filling that in. But the files should be on that website. How effective ASHRAE 109.1 on SRM projects for buildings under $700,000 achievable? 109.1, its scope does say for major renovations and not just new construction. For small projects, especially for SRM work, you're always, of course, going to have the existing condition that'll affect how well you can do certain things. The performance metrics for a major renovation, I've seen in some things where they reduce the levels required, or they acknowledge that they'll end up with a higher energy intensity per square foot. There's only so much you can do. That's something that you'll have to look at the thresholds for the total facility, and if you have a project under $700,000, how big is that in proportion to the entire facility? To see if that qualifies as really, are you doing a major renovation from the 199.1 perspective versus something minor to see if that applies to you or not. But in general, if we look at this as a culture change, trying to do the right thing, then we don't necessarily care what the size of the project is. We just go about it as looking for opportunities to save energy, to do things better, henceforth. And maybe we can't meet maybe we acknowledge that we can't meet the total high bar of a savings for a new facility. That's one thing that people have brought up, is that when we try to hit the net zero for new facilities by 2030, and all this stuff we're doing, that 75% of the building inventory we have then will be buildings that we have now. And so the energy efficiency of these buildings that we have now are something that needs to be addressed, because it doesn't really make any sense to have 25% of your buildings super efficient if the other 75% are just sieves, wasting energy. Have maintenance costs been accounted for in the life cycle and payback analysis? Photovoltaic cleaning, green roof maintenance, etc. Yes, they certainly should be, and that gets back to the part of the standardized life cycle cost analyses, because there's been a requirement from Congress for a long time that we obtain 30% of our hot water generation from solar thermal, and that has typically has people doing cost analyses that say, oh, it's not cost effective, because there's a caveat on there that it says if it's cost effective. Now, granted, natural gas is really cheap right now, but even when it wasn't a couple years back, I saw some life cycle cost analyses that had costs for going up and cleaning photovoltaic panels, which most likely would not be something that would be done. Certainly not at the frequency that they had. I think it was like monthly or something. Generally, you have rain. Rain will wash the things off, but there will be some dust that'll accumulate on the system. But you just derate the panels 5% for their power output, 5% max, based on what you expect for the fouling based on dust and debris. But otherwise, maintenance is reconciled in the life cycle cost analysis. That's part of the process. But we're going to work towards standardizing that and make sure it's not just a tool for trying to get the decisions that you want versus trying to do the right thing. Not that anybody ever would. The question was how to pay for life cycle cost analysis. Okay, this is getting back to the question about life cycle cost analysis versus value engineering. Life cycle cost analyses, we are going to require them for things that go beyond 199.1. So if you're looking at doing an additional system for energy savings beyond 199.1, that would be something that would need to have a life cycle cost analysis done on it during the design process. It's a good point that you make that the value engineering already includes a life cycle cost analysis in that process. But we're looking at something that will be more during the design development phase, making design decisions as you go on, that might be revalidated in a value engineering effort. Also, life cycle cost analysis might apply to things, not just mechanical systems, but roof systems and other things that we're looking at. I hope that answered the question. Ben, send me an email if I'm not following what the question is, and I'll follow up with you after the presentation. We only have 1 minute left, and I have one more question. All right, so you mentioned DCO capacity, and I don't see where. I thought there was a thing where I could say turn on your mic, but that's not showing up for me right now. So anyway, so it is now 4:01, 1 minute over. I will stop the recording and conclude this. I'll stay on for a few more minutes if anybody wants to type any more questions in, but otherwise we will call this a day. Thanks for participating, and I hope that we'll have many more of these sessions and webinars coming up. And that I think this New venue for us, this Defense Connect Online, seems to be working pretty well.